Hello, this is the first of a new series of videos I'm gonna try out as an experiment of small subjects which are not directly part of the learning objectives for any of the ATPL subjects, but help you to understand those subjects. And the first one I'm going to do here is a little bit of physics. You may know I've already done some physics and maths videos, but this is an extra physics video. And the subject's going to be the relationship between power and force. So in aviation terms, really, the relationship between the power of an aircraft and thrust, or the power required, and drag. Okay, so I just share the screen here, and we're going to start out with some very basic physics that I hope you've come across, but if you haven't, I'm not really going to explain it. You can look it up in sort of more of a physics text, but the formula we're going to start with is that work equals force times distance, and this is pretty much the definition, the defining formula for work. But if we define the term work is usually defined as being the change of energy. Okay, so it's the amount of energy that's changed from one state to another is work. Okay, and that is force times distance. So in terms of aviation, we could say that the force might be thrust or drag. So we might say that the work done by the engines is thrust times distance. Okay, so that's the relationship with aviation. Now that brings us on to, well, we want to know the relationship between power and force, not work and force, but power is just defined as the rate of change of energy. Rate of change of energy. Well, of course, we just said that the work is change of energy, so that i.e. it's a rate of work. I'm putting that in equation form. That means that power is a rate of work, which we would take the work and the total work and divide by time. Now, yeah, someone who really knows the physics would say yes, but that's only the average power. We're assuming here a constant power because we're just going to take effectively instantaneous power. We're just going to take power at any one moment. So within this equation, we're saying that the power is constant. So take the total amount of work done and divide it by the time taken to do that work. We'll find that's then the rate of doing work, which is by definition power. But we've already said that work is force times distance. So what we've got is force times distance divided by time. Now, you may see I've particularly put time in one place in the equation. I could have done the whole thing over time, but because multiplication and division are equivalent in the order of functions, it doesn't matter what order we do the multiplication and division in. I can happily divide distance by time before they're multiplied by force, or divide force by time before multiplied by distance, or I could multiply force by distance and then divide by time, which is what it looks like it should be. They'll all give you the same answer. So it doesn't matter that I've put the time over here below distance, except that, of course, then I can bracket this and say, well, that whole thing there, of course, is speed. And so in terms of physics, we're going to say that power is force multiplied by speed. Okay, so again, for anyone who's really good at physics, you might notice I'm ignoring a lot of vectors here and directions of vectors. Yeah, we're assuming that the force and the speed are in line and so on. But yeah, because in fact we should be force times velocity. But yeah, we're going for a magnitude of everything here, where everything is in line, because that's how it works in the functions we've got to follow. But assuming everything is in line, power is force times speed. Okay, well that's useful. I'm going to scrub all this to get space and put that at the top. So power equals force times speed. Power equals force multiplied by speed. Great. So how is that useful in aviation terms? Well, the first thing to think of, one of the obvious forces we've got is thrust. So if we want to consider the power output of an engine or a pair of engines or 4 engines, whatever we've got, then we can take the total force they produce. Well, we call that force thrust, don't we? The force produced by engines is known as thrust, and multiply it by the speed of the aircraft. But we've got to multiply it by true airspeed, because of all the air speeds, ignoring ground speed, all the air speeds, because this is where we're considering how much power we're putting on the air. Only TAS is actually a speed. So IAS, CAS, and EAS are all pressure differentials. In fact, they're not speeds at all. They're pressure differences which are calibrated for convenience as speeds, and which we can convert into a speed we call TAS, but they're not actually speeds. Now, this explains to us why, when you see a power curve, you'll usually see power against TAS, or power required or power output against TAS, whereas when you see thrust and drag curves, you see drag or thrust against IAS, CAS, or EAS. They have a bad habit of sort of randomly choosing one of those three. To be honest, it doesn't really matter that much which they choose, but it's usually against either IAS, CAS, or EAS if you're looking at drag. So our power output is thrust times TAS, and the other one to consider is our power required. And when we say power required, I should say power required straight and level, because this is the power we require to produce to maintain straight and level for the aircraft. So that means that our thrust is just enough to overcome our drag, and not more than that, which would allow us to climb or acceleration, but to maintain speed and overcome the drag and maintain level flight. The power required, well, the thrust required then is the same as drag. Again, we're ignoring direction, we're ignoring the vectors, we're just taking the magnitude of the drag. So if you take drag multiplied by TAS, that's going to give us the power required to maintain straight and level. Anytime you see power required, it's always power required to maintain straight and level. Yeah. Okay, so that's actually quite interesting, because it tells us a couple of things about the power curve and the drag curve. Two things to take from here: power output of the engine is always going to be thrust times TAS, and the power required to maintain straight and level is always going to be drag multiplied by TAS. Okay, let's stick that at the top, and then consider the graphs of drag and power. Now, the power one is slightly hard to draw once I've drawn the drag one, so I might have to have a couple of goes at this. Right, so what I'm going to draw is a graph here initially of the drag curve, and in fact I'm going to use 2 different scales, vertical scales. The horizontal scale, for simplicity's sake, so we don't need to bother about whether we're using CAS, EAS, or TAS. We'll assume that these graphs apply at the graphs we're going to draw today are going to be at sea level and ISO, so at 0 density altitude, 1.225 kilograms per cubic meter air density. So this is CAS across the bottom, and it also is the same as TAS at 0 feet density altitude. Just for simplicity's sake, because remember I said we tend to draw these things against different, the drag and the power against different speed measurements. Okay, so the first thing I'm going to draw is the drag curve. So on the vertical axis, I'm going, excuse me, I'm going to say this is, sorry, my writing's not very good, drag. Okay, and I hope you're familiar with the drag curve, which, if I get that to go something like this. So drag starts relatively high at just above the stall speed. It comes down to a minimum drag speed and then starts going up again. Yeah, so when we've got very low speeds and induced drag is dominant, we've got high drag, we've got very high speeds, and and parasite drag becomes high, we've got high drag again. But where parasite drag and induced drag are equal, we've got our lowest, and that's our VMD. And if you want to see a more accurate version of this, in some of my videos, I do use a more accurate version, which I've done with Excel to show it's actually square relationships and so on as it should be. This is good enough. This is what you're likely to see in class, and it's perfectly good enough to learn. Okay, so that's our drag. Now, if I want to draw a power required curve, so this is going to be power required. Again, power required means power required straight and level, so it's going to be drag multiplied by TAS. Okay, now let's see if I can draw a decent one of these. There's a couple of important points about it, one of which is slightly hard to draw. Okay, so it's going to come down like that, and actually that might have worked. I'm just going to quickly draw in a tangent to this curve. Yeah, it's not working. Sorry. I'm just going to pause the video and draw this because it's a pain to draw. Right, that's better. So yeah, I've drawn this. There's one particular feature that's difficult to draw freehand, and I'll bring that up in a minute. So okay, so there's really two things we need importantly to notice about this curve. Because of the way it's formed from the drag curve, so we've taken the drag curve, which is drag against speed, and multiplied it by speed. Now, if we're keeping a constant altitude, it doesn't really matter whether we're measuring CAS or TAS because they have a constant relationship. And as I said, we're doing this at zero density altitude, so they are equal. So I've multiplied my drag by the speed, and what that's done is, of course, on the lower end, it's multiplied by a smaller number, and as we get to the higher and higher end, or to the right, it's multiplied by a higher and higher number. So the first result of that is that the bottom of the curve, it's still somewhat of a U-shaped curve, but you can see it's much more smeared up and to the right. And the bottom of that curve, which is the minimum power speed, is always going to be at a lower speed, because we've multiplied these lower the lower end of this curve by lower numbers and multiplied the higher end by higher numbers. The VMD is always going to be to the right of the lowest point, which is VMP. So the VMD is always going to be higher than VMP. That's always going to be the case, whatever power and drag curves you can draw. Okay. Now the second thing is really interesting, and you kind of just need to know it, although I'll explain the maths behind it, because it's a helpful thing to understand how gradients work. I mentioned it. My maths video does a little mention of this. Okay. If I draw a tangent to the power curve, so this is a tangent to the power curve from the origin. Now, if I just mention a tangent to a curve by convention in maths, that's the tangent from the origin to the power curve. So that's a line that's from the origin and just touches the power curve. Yeah. And it touches in one point. If that line was any lower, it would miss the curve entirely. If it was any higher, of course, it would touch at 2 points. This is the point where it touches at 1 point. And that's interesting because the way I've drawn it, it touches at VMD. Yeah, it touches the tangent to the power curve, touches the power curve at a speed of VMD. And that's no coincidence. That's the bit that I had to draw carefully because I want that bit. And why do I want that bit? Well, first off, you can just remember that the tangent to the power curve always touches VMD. But I like to know why. And the reason is that the gradient of any straight line from the origin is the drag or thrust, depending on, is the drag at that point. So a drag at the points it cuts. So let's draw a more arbitrary line. I'll draw it nice and bright. So we say, yeah, that just cuts the power curve and the drag curve. Okay, but it's a power line. Okay, this is not a, this is, we're in the power domain here. This is in units of power, not in units of drag. Okay, so it cuts this cuts the power curve at 2 points. Okay, so there are 2 points in the power curve for which this is a relevant metric. This is a relevant line. Okay, now let's consider this higher one. Now the power required, there I'll call P, and the TAS for that I will call S for speed. Okay, now the gradient of that line is P over S. Okay, so the gradient of any straight line from the origin is going to be the power, the vertical change. Gradient is always vertical change divided by horizontal change. If you're not sure of that, have a quick look at my maths video. I mentioned that briefly in sort of this context. So in this case, it's power divided by speed. Okay, that's fine, and that's we can relate that to this point on the power curve, yeah, because that's a relevant point on the power curve where the power required is P at the speed of S, at a TAS of S. Power required is P. Okay, but the power, we've already said, power is thrust. Right, power required is not thrust, it's drag multiplied by speed, which is TAS. Divide by speed. Well, the speed we're using is TAS. Okay, well, the TAS is cancelled out then. So the gradient of that line is the drag. So any line I draw from the origin, the vertical change is going to be the power, and the horizontal change is going to be the speed. So for any point that goes through on the power curve, it gives the drag. The gradient of that line is the drag at that point on the power curve. Okay, so that's the important thing. So the gradient of any straight line from the origin is the drag at that point. Well, that brings us back to the tangent. The tangent is the lowest gradient. Lowest gradient, and that's the importance of tangents. Again, as I mentioned on the maths video, that's the importance of tangents, is that they show the lowest or occasionally the highest gradient that actually touches the curve. If I can draw a lower gradient than that, but the aircraft can't actually fly straight and level in that condition, it can only descend in that condition because it's missing the power curve. So everywhere along there, for every speed along there, the power is less. If we've got power, this is power available, the power is less than the power required straight level. So that's kind of irrelevant to our curve. This is the lowest gradient that is actually on the power required curve, but the gradient is drag, so it's the lowest drag. Lowest drag. So the point it touches is VMD. Yeah. Now, that's interesting anyway, and you do need to know it, but it's even more interesting when you consider a change of altitude. Now, if we do go up in altitude, one thing to remember is because the drag curve is against CAS, the drag curve doesn't change when we change altitude. Yeah. Now, the power curve is against TAS, and the power curve will change with increasing altitude. But the interesting thing is, because the drag curve doesn't change, therefore minimum drag doesn't change, the gradient of the tangent to the power curve doesn't change, because we've just said the gradient to the tangent to the power curve is the minimum drag. Yeah, it's the lowest drag. So what that means, why that's important, is that if I draw the power curve at a higher altitude, Yeah, so this is we've got the one on the left is a lower altitude and the one on the right is at a higher altitude. The tangent is going to be the same. So the power curve moves along the tangent. Now, for me, that's a far easier way of remembering, because you've got to know that the tangent to the power curve is VMD. That's in fact comes up in a few questions. Well, if you then know that, and you know that the reason is that the gradient is minimum drag, then you can recognize that the power curve, as you climb, the power curve moves along that tangent, keeping the same tangent. What that means is it moves up and right. So the power required increases as you climb, and VMP is going to go to the right. By the way, notice it's gone to the right of the drag curve now, but that's not relevant. I'm now drawing. We kind of got to ignore the drag curve. In fact, I'm going to delete the drag curve. The drag curve doesn't match because that's against CAS, and these power curves are against TAS. Yeah. So now I'm not CAS at all. This is now a TAS only, and I can't. Well, I can draw the drag curve on it, but it's going to go right. The drag curve's gone right as well. In fact, if I measure against TAS, the drag curve's gone right. Yeah. Which is so. The reason I'm saying that is VMP is still less than VMD. So the speed for minimum power has gone up as a TAS, yeah, but it's still less than the speed for minimum drag. Yeah, the only exception to that is absolute ceiling, where they're the same, because you've only got one speed you can fly. So minimum power is minimum drag. It's the only power, it's the only drag you can fly straight up. So until you get to absolute ceiling, when they come together, that's a topic for another video, but then minimum power speed is always less than minimum drag speed. But if we're just considering the power curve, as you climb, the power curve goes to the right, but it follows the tangent, so it goes up and to the right, yeah, with the same tangent. And I think that's interesting, and it's also easier to remember to my mind what happens to the power curve as you climb. It's measured against TAS, it kind of goes up and to the right. Okay, excellent. So that's the relationship between forces and power, and that's it related to thrust, drag, and airspeed. And I hope that's been helpful. If you have any questions, please do contact me. You can put comments below the video, or you can contact me by email, or on the Facebook page, either ATPL Tuition page or ATPL Virtual Classroom Facebook group. And I'm even ATPL Tuition on Twitter if you need as well. But thank you very much for your attention, and I hope this is helpful to everyone.